Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, what we have seen so far is basically we have seen the diversity aspect of a wireless communication system with multiple antennas. Now, what we want to understand is we want to understand how to characterize the diversity of a system. So, we have seen so far that the bit error rate decreases with diversity . But how to characterize diversity? So, as to speak, how to characterize diversity or how to measure diversity of a, how to characterize the diversity or how to measure the diversity of a system, and this is basically given by the diversity order of the system. And how is it defined? We are going to now define the diversity order, which is basically a characterization of the diversity of a system. The diversity order D can be defined as follows: D equals minus limit SNR tending to infinity log of PE SNR divided by log of SNR, where PE SNR, this quantity where PE SNR denotes the probability of error as a function of SNR. Where PE of SNR denotes the probability of error as a function of SNR. So, the diversity order of the system is minus limit SNR tends to infinity, that is at high SNR, log PE over PE of SNR divided by log of SNR. So, this is the definition of the diversity order of the system, which characterizes the diversity of a system. Let us for instance take a simple example. Consider a wireless system. Let us consider a wireless system with L equal to 1 antenna, with L equal to 1 antenna, and we want to ask the question, what is the diversity order, of this system with L equal to 1 antenna, and we can see that for this system the probability, the bit error rate, the probability of error, we have already derived it, is approximately equal to 1 over twice SNR at high SNR. Remember, this is at high SNR, PE of SNR or the probability of error with respect to SNR is 1 over twice SNR. Therefore, the diversity order of this system is D equals minus limit SNR tends to infinity or SNR tends to infinity log of PESNR divided by log of SNR, which is equal to minus limit SNR tends to infinity log of PE SNR equals 1 over twice SNR divided by log of SNR, which is equal to minus limit SNR tends to infinity. Now, log of 1 over twice SNR equals minus log SNR minus log 2 divided by SNR divided by log of SNR, which in turn is equal to bringing the minus side inside, limit SNR tends to infinity, log of SNR divided by log of SNR is 1 plus log of 2 divided by log of SNR. So, at high SNR we have the diversity order given as limit SNR tending to infinity 1 plus 2 log of 2 divided by log of SNR. Now, you can see that log of 2 is a constant, and therefore, as SNR tends to infinity, log of SNR tends to infinity, therefore, log of 2 divided by log of SNR, this quantity tends to 0 at high SNR or as SNR tends to infinity. Therefore, we have the diversity order basically equal to limit SNR tends to infinity of 1 plus log of 2 divided by log of SNR, and we said this quantity log of 2 divided by log of SNR, this tends to 0. Therefore, the diversity order is equal to 1. So, the diversity order of a system with a single receive antenna. So, this is the diversity order of a system for L equals 1 is D equals 1. That is the diversity order of the system of a wireless communication system in which the bit error rate at high SNR decreases at 1 over twice SNR is 1. The diversity order of a system with a single receive antenna is 1. Now, let us see what happens as the number of antennas increases. For a system with L antennas, consider a system or a wireless system with L antennas, and in this case we know that the probability of error P of SNR at high SNR equals 2L minus 1, choose L 1 over twice SNR raised to the power of L, which is 2L minus 1, choose L 1 over 2 to the power of L times 1 over SNR raised to the power of L. Let us now look at the diversity order of this system. D equals minus limit SNR tends to infinity log of PE SNR, but PE SNR the probability of error is 2L minus 1, choose L 1 over 2 to the power of L 1 over SNR raised to the power of L divided by log of SNR, which is equal to minus limit as SNR tends to infinity. I can split this as minus L log of SNR plus log of 2L minus 1, choose L 1 over 2 to the power of L divided by log of SNR. Now, bringing the negative side inside, this is equal to limit SNR tending to infinity, L log SNR divided by log SNR, that gives L minus log of 2L minus 1, choose L into 1 over 2 raised to the power of L divided by log of SNR. Now, you can see that this quantity log of 2L minus 1, choose L times 1 over 2 raised to the power of L, this is a constant. So, this constant divided by log of SNR, as SNR tends to infinity, this quantity here tends to, so this quantity tends to 0 as SNR tends to infinity. Therefore, we are left with this quantity L. So, the diversity order equals L as SNR tends to infinity. Therefore, diversity order of the system with L antennas is basically equal to L. So, diversity order of the system with the diversity order of a system with L antennas is equal to L. Now, let us look at another interesting scenario and let us look at the diversity order of the AWGN or the wire line channel. What is the diversity order of the wire line system? Let us ask this question, what is the diversity order of the wire line system or the simple AWGN channel. We know that the probability of error for the wire line system, probability of error as a function of SNR is equal to Q square root of SNR, which at high SNR is approximately equal to half e raised to the power of minus half SNR. At high SNR, this is approximately equal to half e raised to the power of minus half SNR, and therefore, our diversity order, therefore, the diversity order D equals minus limit SNR tends to infinity. In the numerator, we have log of PE, that is probability of error, which is half e to the power of minus half SNR divided by log of SNR, which is minus limit SNR tending to infinity log of half minus half of SNR. Consider the logarithm to base e, log of e to the power of minus half SNR is minus half SNR divided by log of SNR. Now, this quantity log half is a constant. So, as SNR tends to infinity, log half divided by log SNR, that is 0. So, this is equal to minus limit SNR tending to infinity, or bringing the minus side inside, is equal to limit SNR tending to infinity half of SNR divided by log of SNR. Now, you can see in this expression both the numerator and the denominator tend to infinity, that is SNR and log of SNR tend to infinity. Therefore, this is an indeterminate form. So, to compute the limit, I can use the L'Hopital's rule. So, that is basically differentiate the numerator and the denominator. So, basically using the L'Hopital's rule, what we have is the diversity order D equals limit SNR tending to infinity, and I am now going to differentiate both the numerator and the denominator. If I differentiate the numerator, I have half SNR, the derivative of that with respect to SNR is half. On the denominator, I have log of SNR, the derivative of that with respect to SNR equals 1 over SNR, which is equal to limit SNR tending to infinity of SNR divided by 2, which is equal to infinity. That is, limit SNR tends to infinity of SNR divided by 2 is infinity. So, therefore, the diversity order, so this says diversity order of my simple AWGN channel or wire line is equal to infinity. That is, the wire line channel can be thought of as comprising of an infinite number of independently fading links. That is, the diversity order, which is the number of basically related to the number of independently fading links, is infinity for the wire line channel. So, it can be thought of as the combination of an infinite number of independently fading links. So, the AWGN channel, so this basically means AWGN channel is basically a combination of infinite independently fading links. So, what this tells us is that the diversity order of the AWGN channel or the simple wire line communication system with no fading is equal to infinity. Therefore, this can be thought of as, or this can be thought of intuitively as a channel with an infinite number of independently faded links, which gives rise to a diversity order of infinity. Alright. So, that basically concludes this module on diversity order, and we have comprehensively looked at several aspects of multi-antenna wireless communication systems, such as what is the optimal combining, which is given by the maximal ratio combiner, the bit error rate performance, the deep probability of deep fade in the system with multiple antennas, and finally, now we have also derived the diversity, characterized the diversity order of different wireless communication systems. So, we will conclude this module here, and we will explore other topics in subsequent modules. Thank you very much.